Okay, so I wanted to do another little example having to do with graphing, position, velocity, and acceleration graphs with a story similar to some of the work that you've done in your practice problems. So let's imagine we are heading to the waterfront, local establishment up by Lake Monoman to enjoy some lunch, and you live on South Campus. So we're going to describe your path graphically from South Campus to the waterfront. So let's say that in that path you start at your dorm, you begin walking, speeding up at a steady rate until you reach your maximum walking speed. You get close to the waterfront and then start to slow down to a stop at the door. All right, so what might that look like? So I'm going to share a screen with you to look at how we might develop this graph. Okay, so here's our story about going to the waterfront, and we have the three graphs laid out: velocity versus time, position versus time, and acceleration versus time. Now, what I typically like to do is start with the velocity versus time, sort of that, what is the motion looking like as I make this trek from South Campus, up to the waterfront. So it says that I start walking. So if I start walking, that means I've started at 0 and I'm going to begin walking. So at the beginning of the time I'm interested in, my initial velocity is going to be right at that axis, at 0. I start to walk. So I must have been not walking ahead of that time. Tells me that I start walking, speeding up until I reach my maximum velocity. So if I'm speeding up, my velocity is getting bigger and bigger and bigger. Now that, and if it's at a steady rate, like I said earlier, it's getting bigger and bigger and bigger in a straight line. Okay, but I gotta figure out, is that straight line numbers getting bigger and bigger, getting bigger and bigger in this direction? Or are they getting bigger and bigger in this direction? Because as time goes on, if I am moving in the positive direction, my numbers would be increasing along the positive axis. And if I'm moving in the negative direction, my numbers will be increasing along the negative axis. So what am I doing in this story? It tells me that I live on South Campus and I'm heading to the waterfront, which is directly north of my dorm. So I am moving north, or positive, as I move from my dorm to the waterfront. So if I'm moving in the positive direction, my motion is above the velocity versus time axis. So I start out at that 0 velocity, moving in the positive direction and speeding up. My numbers are getting bigger and bigger and bigger as time goes on. And if it's at a steady rate, it's a nice straight line with a slope. All right, it then says that I reach my maximum walking speed and I walk at that speed for a bit. So now my velocity is no longer changing. I'm still heading in the north direction, and so I will have a steady velocity heading in the north direction, positive direction. It then says as I approach the restaurant, I slow down at a steady rate, coming to a stop. So that means my velocity is decreasing in magnitude. I'm slowing down, and therefore my velocity numbers are getting smaller and smaller, but I'm still heading in the north direction because I'm heading to the waterfront. And so my numbers start to decrease until I come to a stop, meaning no velocity. And there I am at the door. So a couple things that we want to notice in this graph, and to check if it matches our story. I start off walking, speeding up. So right as I step my foot out the door, I'm starting at 0 velocity and increasing my velocity. My numbers should be getting bigger. And then since I'm heading north, they should be above the axis. So now my numbers are getting bigger as I head north above the axis. Then I am walking at a steady rate. So my velocity isn't changing as time goes on. So I have a horizontal velocity here, representing that I am not changing my velocity as time goes on, horizontal line. And then I'm going to slow down as I approach the door. And I'm slowing down pretty quickly because I have a nice steep slope. My velocity is decreasing, but I'm still heading towards the door, which is north. So I'm still in the positive side of the velocity time graph until I stop, and then my velocity is 0. All right, so now once I have my velocity, I can go either to acceleration or to position. Doesn't matter which we do, what order we do it in. Let's go to acceleration. So during this speeding up time, my velocity slope is positive, and the slope is the acceleration. So the slope of the velocity graph is my acceleration. So that's one way we know that our acceleration during this time should be positive. So above the axis in the positive side of our acceleration graph. Now, another way we might know that it should be in the positive side of our acceleration graph is that I am heading in the positive direction, north, and I'm speeding up. So I'm heading in the same direction as my acceleration. That's what gives rise to speeding up. And so if I'm moving positively, my acceleration also has to be positively. So two ways to get our direction of acceleration. Because it's a steady increase in speed, that straight line, I have a steady, a constant acceleration. I then am moving at a constant velocity. Well, constant velocity is no acceleration. So my acceleration then should be represented as nothing, 0, constant velocity, no acceleration. And then I start to decrease my speed in the positive direction. We'll use those two methods again to determine where that acceleration graph should be generated. First, I have a negative slope. And since the acceleration is the slope of the velocity graph, my acceleration should be below the line. And you can see that I made it further below the line than I did on the speeding up portion of the clock. Why? Because this is a much steeper slope. It has a higher acceleration than this more shallow slope. So higher acceleration, larger number, lower on the graph. All right, the other way we know it's going to be below the axis is because I'm moving to the right, but I'm slowing down, as the description tells us. Well, then our velocity and our acceleration have to be in the opposite direction. That gives rise to slowing down. So that's how we move from our velocity time graph to our acceleration time graph. What about our position? Well, in order for us to accurately represent the position versus time graph, we need to identify the origin, because remember, position is all dependent on where we set the origin. So if we were to set the origin at the waterfront, where do I start? So we're going to first identify with the purple pen, this first drawing, where the origin is at the waterfront. I'm actually going to do two different origins to show you that for a position graph, the shape of the graph doesn't change, but the location of it does. So if the origin is at the waterfront, then I am starting at my dorm south of the origin. So I'm somewhere in the negative world. Let's just say I'm here. This would be my dorm, and this would be the waterfront. And I'm going to abbreviate that H2O. Now, over these first 3 blocks, okay, I am speeding up. I'm speeding up, and I'm moving in the positive direction. So my motion is going to be towards the waterfront, positive direction, and speeding up, meaning that I'm getting faster and faster and faster, which means that my slope of my position versus time graph is going to get steeper and steeper and steeper, because the slope is the velocity. So I cover more distance for every small time frame as I get faster and faster. So as I start out, I cover a little bit of distance, maybe just this small amount. And as I continue to move, I cover more and more distance during the speeding up phase. So in this amount of time, this first square, let's say, I covered this amount of distance. In the second amount of time, well, I covered this amount of distance, more distance. I got faster. In the third block of time, I covered this amount of distance, more distance. I got even faster. So I'm speeding up. And we see that sort of this curvilinear shape on the position versus time graph. Then I head at a constant velocity. Oh, this is not a good drawing. I'll just, this is not a good drawing. I'm too steep here for the time frame that I've given myself. So we actually, I have to erase that a little bit. I'm going to keep the video going because this is sometimes ways we check our errors, and so that's always good to think of too. So if I need to move at a constant velocity, so I have to have the same steepness at this area, and I don't have enough space for that given my thing. So we're going to have to make a shallower graph. Let's make a shallower one. It's still increasing. But then at this point, I can move my 2 time frames at that constant rate. All right, so we still have our curve. And then once we hit that speed, we continue at that constant speed. It's a straight line now, represented by a steady slope for the next 2 time periods. And then I have this one quick time period where I'm slowing down. So now I start out at this speed, but I slow very quickly to reach the waterfront over that single time period. I slow very quickly over that single time period. So I'm speeding up. I have this curve, then I head at a steady rate, and then I slow down until I reach the waterfront. And so how does the slowing down work? Does it match our velocity, and does it match our acceleration? I didn't stop my acceleration in the right spot. I'm going to fix that too. Okay, so I am increasing my slope on the position curve. The slope represents the velocity. My velocity is increasing. The slope is positive. My velocity is positive. I'm above the axis. So that's consistent. I then hit a steady rate where my slope is straight. It's that rate right at the end of my speeding up period. And so my steady velocity is occurring. Then my slope starts to decrease as I slow down, and it's negative. I'm sorry, it's still positive. It's positive, it's positive. It's positive as I start to slow down. And we see that decrease in the velocity graph. So position to velocity to acceleration for this story. Now that is what I said if I set the origin at the waterfront. But what if I set the origin at my dorm? How will the graph look if I set the origin at my dorm? Well, then my dorm is here at this 0 spot, and that's where I'm starting. Where's the waterfront? Well, it tells me that the waterfront is north of South Campus. So we'll use the same blocking, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. The waterfront is going to be up here in the positive world because I'm south of it, okay? So how does my motion look as I head from here to this location in the motion story? Well, I initially start to increase my speed. If I start out going a low speed, but I get faster and faster and faster and faster and faster and faster until I hit my top speed, at which point I travel at that top speed for a little bit, and then I start to slow down, so I make less progress in the position over time, and I curve in this way. So here's that curve, straight, and this curve. Now, how do these two graphs compare? They look the same. So the graph of the position versus time curve is going to look the same regardless of where we set the origin. So the location of that motion depends on where we set that origin. The shape of that graph is determined by how the motion itself is happening. So This motion story, we described moving in the positive direction, speeding up at the beginning, moving at a steady rate, and then slowing down. Again, we looked at the velocity versus time graph first. I find that one easier to draw initially. Paying attention to the direction of motion, which was always to the north, so above the line, and paying attention to whether I'm getting faster, my velocity numbers are speeding up, getting bigger, whether they're not changing, constant velocity, or I'm slowing down, my velocity numbers are getting smaller. Then I can use either my conceptual relationships between velocity and acceleration to determine that representation, or I can look at the slopes directly, which is also a perfectly great way to do it, and utilize that slope information. And similarly, as I move to position. So we'll do another practice problem in another little video. This gives you one example of how to move from velocity, positions, and accelerations. All right. I will stop sharing that screen, and good job.